And finally, here is one last application. This is, again, a new identity. I don't think you have seen it so far. I've seen it on some contests. It's not hard to prove in different ways, in particular by induction. You can prove it as well, but let's prove it combinatorially. N and m shall be two non-negative integers. We claim that n equals sum from k equals 0 to m minus 1, n minus 1 choose k plus 1 factorial over n to the k plus n minus 1 choose m factorial over n to the m. I will not say that this is a particularly beautiful identity. There is a way to make it nicer by like applying it to m equals n, in which case this term disappears because it's 0. But actually the general case is more general, so I'm gonna sacrifice a little bit of beauty for generality. I claim that this can be proved combinatorially. Well, first of all, how? Isn't this a fraction? This is not an integer, so it doesn't count anything. Okay, it doesn't, but this is not a big deal. In fact, multiplying both sides with n to the m, we can rewrite this as n to the m plus 1. 1 over n to the k becomes n to the m minus k, and this just becomes nothing. And if you look at it, if you're a little bit more careful, you see that there is an n factor everywhere here. So actually, we shouldn't have multiplied it with n to the m. One less copy of n is enough. So let's divide it again by an n. You can see easily that everything is still an integer. And now everything is an integer and positive and non-negative integer. So there is a chance of a combinatorial proof. So we prove this by double counting again. Specifically, we shall double count the number of m tuples of elements of n. So a1 up to am should be elements of the first n positive integers. Okay, so first way, well, clearly the number of such m tuples is n to the m. So the left-hand side is explained, half our job is done. Second way, let us break up this kind of tuples in such a way that you count them by this right-hand side. So obviously, this sum over k means that each of those m tuples should have some kind of quantity between 0 and m minus 1, or maybe it can also be m, but this is like a missing addend for this sum. It just doesn't exactly fit into the sum, but it looks like it should be a missing addend. So the definition of, so the way how we exactly break up this count is interesting. We define the width of an m tuple a1 ... am to be the largest I, let me say 0 in 0 ... m, such that a1, a2 ... ai are distinct. So if you look at the general m tuple, its entries are not usually distinct. You will have entries that repeat themselves. But if you look at only the first few entries, they usually are distinct. The repetition has to start somewhere. And basically, the width is the point where the repetition starts. So, for example, the 5 tuple 1, 4, 2, 2, 1 has width 3. Why? Because the first 3 entries are distinct, but the first 4 entries are no longer distinct. And there are a few more examples like this. The 6 tuple 1, 2, 3, 1, 2, 3 also has width 3, because 1, 2, 3 are distinct, but 1, 2, 3, 1 are no longer distinct. And for example, the 5 tuple 2, 4, 6, 8, 9 has width 5. In this case, all the entries actually are distinct. So the first 5 entries are distinct. It's clear that you cannot get any further than that. It's already the largest possible possible I. Okay. Note that the width is always a positive integer, unless I guess m equals 0. But well, but we assume that without loss of generality that m is not 0, because frankly, if m equals 0, everything here is kind of obvious. The sum is empty, and this is just 1, so this is saying n equals n. Okay, and now, by the sum rule, the number of m tuples that we want to count equals the sum of the number of m tuples with any given width. And now it remains to count the m tuples with width equal to I. So let us count the m tuples with a given width. Fix I. How many m tuples have width I? Well, this time we just try to reason ourselves by construction. So an m tuple has width I if its first I entries are distinct, its next entry, ai plus 1, repeats one of these I entries, because if its next entry would also be distinct from them, then the width would be not I, but I plus 1 or larger. So for the width to be exactly I, the next entry has to be non-distinct from that, so it has to repeat one of them. And finally, all its remaining m minus I minus 1 entries, so a plus 2, a plus 3, dot, 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 am, are arbitrary. They can be distinct, they can be non-distinct, they can be whatever. So we can construct such an m tuple as follows. First, we choose its first I entries. The number of options for this is, well, the first entry can be chosen from all the n elements of n. The next entry has to be distinct from it, so there is only n minus 1 choices. The entry after that has to be distinct from the first two entries, so n minus 2 choices, and so on, all the way down to the ith entry, for which we have n minus I plus 1 choices, because it has to be distinct from all the previous I minus 1 entries. Next, we choose the I plus first entry, and this entry has to repeat one of those first I entries. And because the first I entries are distinct, we have I choices, so I. Finally, we choose the remaining m minus I minus 1 entries. And they're arbitrary, so the number of options for this is n to the m minus I minus 1. Every one of them can be chosen out of all n elements. We no longer care about whether they're distinct or repeat anything. All right, so the total number of ways to do this is we just multiply by the dependent product rule. It is this times n minus m minus n to the m minus I minus 1. And this is the numerator of n choose I. So if you divide it by I factorial, this will be n choose I. So this is n choose I times I factorial. Okay, looks good, right? So we have proved that the number of m tuples with width I equals this product for each I. And therefore, our previous computation, you just plug in this formula and transform. Remember, we want to get something like this. Well, n minus 1 choose k. Something already is making sense here. Now it is actually slightly smarter because we have an n minus 1 here, but an n here. It's actually a good idea to use absorption to get this term here to be a little bit more similar to this term. So let me actually do this on this stage already. N choose I by absorption is n choose n is n over I times n minus 1 over I minus 1 by the absorption formula. And this fraction cancels this I factor. So this is kind of convenient. Moreover, this n joins this other n. So it raises the exponent. Okay, good. So this looks a little bit more, it's a little bit nicer. Sorry, it's still a sum. Now you realize that this sum already looks a lot like this sum, but you have to substitute k plus 1 for I. So basically you shift the index by 1. I minus 1 becomes what? K. I becomes k plus 1, and this is n minus k plus 1. So here we substituted k plus 1 for I in the sum. And of course, n minus k plus 1 is m minus 1 minus k. So this is looking a lot closer to this here. Okay, but what about this addend? Isn't this weird that we have an addend here that we are not seeing here? So yes, something is wrong. And this kind of brings us to this to the dangers of combinatorial proofs. All of this was convincing, I hope. Well, but maybe too convincing. If you look at this closely, so we fixed I and we kind of assumed that I is some kind of element between 1 and m. Maybe 3 or maybe 4 or maybe something like this. Does it work when I equals m? Well, what does it mean that the width is m? It means that the first m entries are distinct, and the next entry, am plus 1, repeats one of these m entries. But wait, there is no next entry. The first m entries already give you the whole tuple. So this is an exception to our reasoning. Our reasoning tacitly assumed that after we've chosen the first I entries, there is still one more entry to choose, or maybe more, or two more, or three more. But when I equals m, there is no more entries to choose. And so this part of the reasoning, these two steps don't exist. We don't get to choose the plus first entry. We have already chosen all entries. Game over. And incidentally, this also doesn't exist, but this is fine, because at this point we get some kind of like n to the minus 1. Anyway, yeah, no, this isn't fine either, but neither of these two steps exists. Well, congratulations, we got a mistake. Fortunately, this mistake is pretty harmless, because our argument worked for the first m minus 1 values of I. The only case where it did not work was I equals m. So what we have proved is still true if I is not m. The only exception is when I is m. So when I equals m, a similar argument gives us that the number of these tuples with width m equals, well, it's much easier. It's really just this product. And so it's n minus n times n minus 1 to the dot n minus m plus 1. Which is the denominator of n choose m, so it's n choose m times m factorial. Okay, so now we have to be just a little bit more careful here. Instead of substituting the thing, we have to split the sum into the part before m minus 1 and the lone addend for m, because the formula is different for the first m minus 1 addend and the last one. The first ones are this, and the last one is this. So now you have m minus 1 here, and here you have this here. We can still substitute k plus 1 for I, but now the the border is this, and you still have this term here. Okay. Is it the same? Well, it certainly doesn't look the same. This sum has one more addend than this sum, but also this extra addend is different. So to make these two things match each other, it makes sense to break the last addend out of this sum. So n minus 1 choose m minus 1 times k plus 1 will be m minus 1 factorial, and n to the m minus 1 minus m minus 1, which is just 0. So this is just 1. And of course, this addend is still there. Now we are getting closer. This sum is this sum, and all we need to check is that this is this plus this. And actually, I think I made one more mistake here. When I was breaking out the m minus 1 addend, I should have written m factorial, because k plus 1 will be m, not m minus 1, when k is m minus 1. So, sorry. So working from this side, we break it up like this. Whereas working from the other side, we break it up like this. And now you see why they're equal. These two sums are just identical. And this here equals this here by Pascal's recurrence, because the m factorials are actually the same. And this n choose m is n minus 1 choose m minus 1 plus n minus 1 choose m. So what plays into our hands here is Pascal's recurrence. And again, comparing our two answers, the first one is n to the m, and the other one is this mess that we got at the end. We get our claim. So we get this here, QED. So I'm not going to claim that this is the simplest proof, but in a way it explains this theorem in a way that you could not if you just would induct. And there is also a telescope proof, which is even shorter, but it's completely mysterious. So this proof definitely has a reason to be. And it also taught us to be careful, which is another nice thing. To be strict, this use of Pascal's recurrence itself, I guess it's not properly combinatorial, but you can prove Pascal's recurrence combinatorially if you know that this counts subsets. So I would not hold it against this proof that we use Pascal's recurrence. Either way, we proved this identity.